In this session, we are going to hear from Daniel Ranard on his work with Xiao-Liang on emergent classicality and a bound on the spread of quantum information. He is currently a PhD student at Stanford and moving to MIT for his postdoc. Please, Daniel, the stage is yours.
Thanks. So, like you just heard, this is about a bound on the spread of quantum information and the idea of emergent classicality, and it builds on some work by Brandau, Piani, and Horodetsky from a few years ago, and I'll explain the relation to that as I go on. So I'll start by talking about the way the information can spread in various quantum systems, and then we'll try to look at the unifying theme that gives a constraint on the spreading in all quantum systems. And we'll lead up to a precise theorem statement characterizing this constraint, and then I'll talk about how it relates to many-body physics and the idea of emergent classicality in large systems. So our setup will be some large lattice system. And now let's imagine that we have some region A that is initially decoupled from the rest of the system, and then we allow it to evolve over time with some unitary evolution on the joint system. So as you know, generically, the influence of the influence of A will spread throughout the system. And as it spreads, you often say that it stays contained within some light cone. And eventually, the influence of A will spread all over the system B. And what we're going to be asking in this talk is, what can we learn about A by just examining some local region in B? So we look at one of these regions like R1 or R2 or R3 and ask, what did we learn about A? And of course, it's going to depend on the exact dynamics. So let's look at a few examples to get an idea for this. If the dynamics were just some very long random circuit, then the information about A would still be contained somewhere in the system by unitarity. But in this example, when we look at a local region like R1 or R2, we're not going to learn anything about what the input at A was. And another closely related example is if this were a natural system that we're thermalizing, that's sort of like nature's version of a long random circuit, then again, we wouldn't learn anything about A just by looking at one of these local regions. Okay, another example is what if there was some direct transport of the system A, it just walked over and landed at this region R1. Well, then when we looked at R1, we would learn everything about A, but when we looked at R2 or R3, we wouldn't learn anything about A. So that's another very simple example. A third hypothetical example would be, maybe you thought that A was going to directly transport to R1, but another copy of that information was also going to go to R2. Now we know that that's impossible by no cloning, so we see that quantum mechanics already gives you some constraints on how the information can spread throughout the system. And the final example that I'll list is decoherence. So you can imagine that maybe in some examples of these dynamics, the subsystem A is going to be effectively measured by the environment B, and then the result of that classical measurement could be passed to the different regions R1, R2, R3. So let me focus on this example a little bit more because it's going to be very important for the talk. Here's sort of a toy model of what a decoherence evolution might look like on the joint system. You start with A in some superposition, but then after the unitary evolution, which I'm modeling as some C0 gates here, the system is effectively decohered. And if we look at the reduced density matrix on one of these regions Ri, then after this unitary evolution, we look at this reduced density matrix and we lose the phase information about the original coefficients C0 and C1, and we only learn about the magnitude squared of these coefficients in whatever basis we decohered in. So that's a simple toy example. And now why did I tell you about all of these examples? Well, because the punchline is that in some loose sense, all spreading of quantum information throughout the system, no matter what the dynamics is going to loosely fit into these categories, where if there was any information that spread at all, maybe some of it was directly transported in some sense, and I'll denote a region Q called the quantum Markov blanket, that's what we call it, where the quantum information about A might get directly transported. Or for the rest of the regions in the system, for all the other regions R1, R2, R3, etc., there might be some sort of decoherence in some basis of A, where it looks like A was measured and then some classical message was passed to one of the RI. So as I go on, I'll try to make this a little more precise leading up to an actual theorem statement to see why these categories sort of encompass all the ways that evolution can happen in this system. And as I said before, this builds on some earlier work where there was a very similar style of bound introduced by Brandau, Piani, and Horodecki. And in the present work I'm talking about, the bound is much stronger so that it's more of a monogamy type statement. And it also comes with a constructive argument that allows you to do some numerics on medium-sized systems to learn about exactly how the information is spreading. Okay, so to describe the theorem, we'll put it in a slightly more abstract setting. So we forget any notion of spatial locality. We just imagine we have some input system A, and then we have an output system that's divided into many subsystems. And so these BI are our outputs, and you can think of them as our environment in the picture from before. And we're going to ask, what can Bob learn about A, where Bob is localized at one of these outputs BI? And like I said, the punchline will be that for most of these BI, so for most Bobs at their respective locations, they can only receive classical information about A in some sense. And moreover, that classical information will be consistent in the sense that it looks as if it's been obtained from a measurement of A in a fixed basis, where that measurement basis doesn't depend on which Bob we're looking at. Now, to make this a little more quantitative, we consider our evolution maps like this. We start with the system initially uncorrelated with the environment in some state tau b. We evolve both systems. We trace everything out except one of these Bob subsystems, and then this is the map that we're interested in. And the claim, again, is going to be that most of them look classical in some sense. So let me remind you of some terms so that I can make that more precise. You will know what a quantum channel is, just a map of states from A to B, but maybe I'll need to remind you what a measure and prepare channel is. So that's a special type of channel equivalent to an entanglement breaking channel. And it's any channel that takes this form here. So if there is a POVM, M, and a set of states, sigma B on B, such that we can write the channel like this, then we call it measure and prepare. And this is a special type of channel because, for instance, the identity channel, you could not write like this. And the physical significance of a measure and prepare channel is that it has the simple interpretation of being able to be implemented like this. So if Alice and Bob are A and B, then to implement this channel, Alice can take a measurement of the subsystem A using the POVM M alpha. And then she takes that outcome alpha, she sends the classical outcome over to Bob, and then Bob prepares a state sigma B contingent on that outcome alpha. So channels like this can be physically interpreted as you measure the system, you take that outcome, and then you prepare a state based on that measurement. And now, having introduced that, it's easy to say what the general claim is, which is that for almost all BI, the map from row A to row BI is going to look approximately like a measure and prepare map. And not only that, the measurement that's used, this POVM M alpha, will be independent of the BIs. So for almost all of the BIs, it looks like A was measured in some consistent basis. And now, before I give you an exact theorem statement, let me go through some examples to get an idea for how this works. How could this possibly be true? So one example, like I said before, is just a direct transport. Maybe the the system A is directly transported to the region B1. And in that case, the map from A to B1 will be the identity map, and the map from A to any other BI will be this constant map. And does this satisfy the claim that I made? Well, it does, because I only said that almost every BI was going to, the map to almost every BI was going to look measure and prepare. So whereas the map from A to B1 is the identity map, which is not measure and prepare, it does look measure and prepare for all of the other subsystems BI. Another example is the decoherence example that I gave you before. So in this case, no matter which BI you look at, the map from A to BI will have this straightforward measure and prepare form. And a final example, maybe the most interesting example, is if I did a spin chain evolution. So let me get my pen up here. If I had a spin chain whose sites I called B1 to Bn, and then I attached a qubit A on the left end of the spin chain, say, and then I let the whole system evolve, the claim would be that the information that you can get at BI about A at some later time, for almost every BI, is going to look like classical information in the sense that I wrote down before. And although I can't show you that this actually works analytically, of course, you can check this on a spin chain. So you do this with 10 or 15 qubits, and you can verify that this idea holds. OK, so now I'm about ready to tell you the theorem statement, which is that there's going to be some region Q, which is order 1 size, where, and these are sort of like the exceptions. So for the region Q, there might be some quantum information present about A when you look at the reduced density matrix on Q. But the claim will be that for every other region, R, that's disjoint from Q, you can only, the map from A to R looks like some measure and prepare map. And the intuition about this region Q is that it's roughly the subregion of the outputs that have the most quantum information about A. And the reason that we call it a quantum Markov blanket is an analogy with the Markov blanket term used with probabilistic graphical models and so on, where it's the region Q is blanketing our input region A in the sense that any information about A that's accessible outside of it will sort of factor through this region Q. OK, and now finally is the theorem statement, which I'll dwell on for a second because I think it takes a second to understand what's going on, but it's also useful. So we start with an arbitrary quantum channel from A to B1 to Bn. And then the claim will be that for any epsilon, so that's like a error threshold, and then for any little r, so that's like the size of the output subregions that we want to look at. So for instance, in this picture, maybe we're going to look at 2 output subregions at a time. Then there will be some POVM, that's the measurement on A, and some excluded output subset Q, so that's some subset of these Bs. And Q will be order 1 size in the sense that it doesn't scale with n. So there's some order 1 size Markov blanket independent of the total number of output subsystems. So we could be in the thermodynamic limit of our spin chain, for instance. And this Q will still be order 1. And finally, the statement is that the action of our original channel looks very much like the action of this measure and prepare channel up to error epsilon. So now that I've introduced the theorem, I want to talk a little bit about the proof ideas. Of course, I'm not going to prove it. I'm not going to prove the statement for you. But the reason that I think it's nice to at least sketch some of the ideas in the proof is that A nice feature of the proof is that it leads to a constructive numerical algorithm for calculating what is this quantum Markov blanket region in numerically tractable systems. And one reason that I think that's exciting is that I hope that this method of finding the quantum Markov blanket and doing this analysis could actually be useful for classical simulation of many-body systems. So the fact that there's this constructive algorithm, I think, is very exciting. So the first step in the proof is to translate it into a theorem about states instead of channels. So instead, you prove this theorem about states. So I'm flashing this up on the screen for a second for you, but it's basically the same statement, except instead of starting with an arbitrary channel, we start with an arbitrary state on A and B1 up to Bn. And then the theorem will instead be that for almost any subset of these, the marginal, rho AR, will look approximately separable. So on the right here, this is just a separable state. And you might be thinking that this theorem almost just looks like monogamy of entanglement, because it's basically saying that for this large system, for almost any region R that you look at, A looks like it's not entangled with R. So in that sense, it is a statement of monogamy of entanglement, but it has an extra special feature, which is important for our analysis, which is that when you write it as a separable state like this, the row A's, so the ensemble that we use on A to write it as a separable state, doesn't depend on what output region we're looking at. So at what region R we're looking at. So in a sense, it's like A is classically correlated with most other subsystems, and moreover, it's classically correlated using the same generalized basis or the same ensemble. So that's the sort of consistent measurement picture that we're getting when you talk about it in the channel language. And the reason that the theorem for states will help us prove the theorem about channels, some of you will have easily guessed, is that there's this channel state duality. So let me remind you that anytime you have a quantum channel, you can consider its choice state just by acting the channel on a maximally entangled state, on one half of a maximally entangled state. So that gives you some state that uniquely encodes whatever your channel was. And the really nice thing about channel state duality is that constraints on dynamical properties of the channel, so for instance, no cloning, are directly equivalent under the duality, so to speak, to constraints on the static correlation properties of states. So if you've never thought about this before, it's pretty neat to note that no cloning, and which is a statement about channels, and monogamy of entanglement, which is a statement about states, are actually directly equivalent statements if you write them in their simplest forms. So you can prove one from the other. And for our purposes, we're trying to prove how reduced channels, meaning channels where you trace out the outputs, you trace out some of your outputs, reduced channels being measure and prepare is equivalent to the reduced states of the associating choice state being separable, because a measure and prepare channel is equivalent to the choice state being separable. So you can see how there's this sort of dictionary, and we can translate between the channel statements and the choice state statements. Okay, now I'll just say a tiny bit about how to prove the theorem for states. And I'm not going to prove it, but I will tell you a sort of warm-up statement that's illustrative for how you prove things like this. So first, I've just thrown up these definitions to remind you of entropy and mutual information and conditional mutual information. And now let me say what the warm-up result is. So this is not quite the theorem about states, but it's similar in spirit. We say that for any state on some subsystems labeled A and B1 to Bn, and for any size little q that you're interested in, we can find a region of the outputs, or sorry, a subset of the subsystems where the number of subsystems is less than little q, such that A doesn't have large conditional mutual information with any other BI conditioned on Q. So I know this is a lot of symbols, but the message is that the conditional mutual, you can find some region Q such that A has small conditional mutual information with almost everywhere else in the system once you condition on that region Q. And this is very easy to prove, and it's sort of a baby statement of what we want to prove. And the way that you prove it is like this. So you can use a sort of greedy algorithm to prove a statement like this. And you do it as follows. You say, okay, I want to build up this region Q. So I'm going to build it up one by one. So I'm going to start by finding some B that I'm calling B I sub 1 that maximizes the mutual information of A with BI1. And then you're going to find another B, so some BI2, that maximizes this conditional mutual information. So you're at every step you're greedily asking, how can I increase my mutual information with A? How can I get more information about A by adding more and more regions to this, by adding more and more subsystems to this region Q? And then by the chain rule of mutual information, we know that all of these terms that we maximized in our greedy algorithm can have at most 2 log, their sum can be at most 2 log dA, just by the chain rule of mutual information. So strong subadditivity tells us that all these terms are positive, and meanwhile, they have some upper bounded constant fixed sum, which means that at least one of the terms is small, because you can't add up a bunch of medium-sized numbers and get a small number. So at least one of them is small. And then whichever small term that is, that allows you to define your region Q. Okay, so again, this was just sort of a warm-up, but it gives you a flavor of the constructive proof. The difference between this statement and this actual theorem statement that I told you about before is that the actual theorem statement will need to involve some extra classical conditioning on the region Q that we didn't discuss here. Okay, now that I've dragged you through some of the proof ideas, let me zoom out and talk about why this is interesting. So what this theorem does is it identifies some basis, or I'm calling it a basis, but really it's a POVM. It could be a PVM, in which case it's a basis. It's some basis on A that is effectively measured by the rest of the system. So this doesn't always happen. I mean, the dynamics could be trivial. So you could apply this theorem even to the identity map, in which case no information about A would proliferate through the system. But the idea is if any information about A at all spreads around in the system, then you'll be able to identify this effective basis in which A was measured. And physically, this is interesting because it corresponds to our picture of how classical variables emerge in many-body systems. So let's say this is a big tub of water and it's undergoing some complicated quantum dynamics, but we expect that even though the huge Schrödinger equation is very complicated, there are some classical hydrodynamical variables, like the local water velocity, for instance, that are actually obeying some classical equations of motion. And these are the sorts of variables that are being decohered naturally by the dynamics. And again, when I say decoherence, I don't mean that there's some wholly external measurement apparatus that's doing the decohering. I just mean that the subsystem A is being internally decohered by the other subsystems in our larger system. So using so as I was saying before, the proof method that I discussed leads to a sort of greedy algorithm for actually finding what this quantum Markov blanket is, this region Q, but also finding what this POVM M is. And I'm hoping that by finding those in some systems, you can both get a better theoretical understanding of which variables are decohering within your system, but also it could help you in simulating your quantum system on a classical computer. So I'm nearing the end. I'll just mention a few general areas for future work. Of course, the first question might be, how tight is the bound? And I have no evidence that this bound is tight. In fact, I believe it can be improved. Although if you compare to quantum Definetti theorems, you can see that in some ways it is tight. So there are some dependencies that probably cannot be improved. Also, this relates to compatibility theory. So maybe you've heard people talk about this idea of compatibility, which is to ask for two different channels, when are they compatible in the sense that you can find them both as the reduced channel of a given parent channel. So this is an interesting question, and you can reframe the result I presented to you as a sort of approximate compatibility result, saying that whenever you have many channels that are all compatible, then most of them needed to be approximately measure and prepare. Okay, I'll leave it at that and see if there's any questions yet. Thank you.
Okay, thanks a lot for this great talk. So I have a few questions myself, but I will start the questions from the chat. Michael Oliveira asks that, to which point can you use your theorem on a quantum algorithm, on the circuit model, for example, to create the quantum Markov blanket for a specific qubit?
Yeah, great. So of course, when a quantum algorithm runs in your quantum computer, it doesn't seem like anything very classical is happening. So how can we reconcile that with this theorem? Well, if you pause your quantum algorithm in the middle before its answer onto one of the qubits, then probably the state is some complicated state. And if we look at the marginals on any of our qubits, they're likely to be to look sort of random or to look maximally mixed. So the first answer is that if you sort of stop a quantum algorithm in the middle of its running, then it probably looks like this thermalization example that I discussed, or like this long random circuit example, where in fact none of the output subsystems are learning anything about whatever your input was. However, if you stop the quantum algorithm after it's finished, then maybe if your output of the algorithm was some deterministic value on the first qubit of your register, then when you look at the map from A to that first qubit, you might get some measure and prepare map, but when you look at the map from A to any of the other qubits, you'll probably get a constant measure and prepare map that's more like the thermalization example.
Thanks for the clear answer. So I myself have a question, actually two questions. The first question that I have is that at some points in your slides, in the statement of the theorem, the size of Q was bounded by, yeah, maybe that was a typo. Yeah. So for example, in this statement, the size of Q is upper bounded by dA square log dA.
Yep.
But later on, it's just log dA. So which one is correct?
Great. So I guess there are two related but slightly different statements being made. So the first time you saw it, it was in the channel context, where I'm saying that the reduced channel onto outputs look approximately measure and prepare. And there you're going to have extra dimensional factors, so it's a slightly worse bound. Whereas over here, when I make this statement about states, then you're going to lose that dimensional factor. So you're going to get a slightly better bound. And you're going to do that by using the one-way LOCC norm, which I didn't have time to introduce, but it's a method. I hope I get this right. I think it was first used by Brandau and Harrow and some others to do these sorts of proof methods.
Yeah, thanks. I mean, it makes a lot of difference, if, for example, dA scales with the system size, then suddenly Q can encompass the whole system versus only a small part of it.
Yeah, it is very important, and I would love to try to improve this dimensional factor dA here, because that means that your bound stops being very good if you have more than a handful of qubits. So, sorry, a handful of qubits for your region A. The environment B can even be infinite, and this bound will still be good.
Okay, I actually have one more question, but there is one more question in the chat, so I will go for that. Dao Chen says that you briefly mentioned quantum definity theorems at the end and how that makes you think the bound is tight. Can you elaborate a bit more on that, please?
Yeah, great. So definity theorems, many of you know, will characterize permutation invariant states. So one version of a definity theorem is to consider a state like this, row A and then B1 to Bn. So that looks like the sort of states I was considering, but they additionally assume that the state is permutation invariant with respect to switching around the B's. So they have a stronger assumption, but then they prove a sort of similar statement, like they show that for all of the BI, that the marginal ABI is close to separable. So you can think of what I've shown you as a sort of non-permutation invariant generalization of the definity theorem. And the bounds are slightly weaker, although the assumptions are much weaker because we don't use permutation invariance. So if you stare at these expressions and compare it to the ones I was showing you before, you can see the similarities. I don't have time to point it out right now, I guess.
Okay, thank you. There are a few more questions in the chat, so if you can go ahead and maybe try to answer them there, or otherwise, if you want to meet Daniel in person, there's going to be a roundtable discussion at 5 p.m. Central European time, and that finishes our talk and the session. Thank you very much.